Okay, so the other type of system that we often see when we're talking about a simple harmonic motion is pendulums. And specifically, we're talking about pendulums that are not rocking back and forth too far. So as long as the angle in which they are oscillating is 10 degrees or less, then they're pretty good example of simple harmonic motion. If the angle gets bigger, then we can't really consider them to be simple harmonic motion anymore. So in this case, we've got a pendulum on the moon, and we want to know how long it has to be. So we've got a pendulum on the moon with an acceleration due to gravity on the moon of 1.6 meters per second squared. If the pendulum on the moon has a mass of 2.3 kilograms on the end, and it has a frequency of 0.5 hertz. How long is the pendulum? So I always like to write down everything that I am given. We weren't necessarily going to use it all, but it's good to sort of pull it out of the question. Anytime we are given a frequency, I like to change it into a period, since all of the formulas that we're going to be working with here involve periods. So remember, period is equal to the inverse of frequency, 1 over frequency, 1 over 0.5 hertz. So our period here is going to be 2.0 seconds. Again, as I said, we're assuming that this is a pendulum that is not oscillating back too far. So we're going to go ahead and use this equation here, where the period is equal to 2 pi times the length divided by the acceleration due to gravity. In this case, we are going to be trying to isolate for this length here. So we have the acceleration due to gravity and we have the period. You notice that this mass up here, this is extra. We don't need that mass. It's just there to try and trick us, so don't get fooled. So first thing we're going to do here in order to isolate the length, well, there's a couple different ways we could do this. I'm going to start by squaring both sides. So t squared on the left. On the right, we can square each part separately. Basically, we're going to distribute the exponent to all three parts in here. So we have t squared times pi squared, 2 squared times pi squared, times L over G. Since we're looking for L, again, I'll highlight that here. Well, we need to get rid of this 2 squared, and we need to get rid of this pi squared and this g. So let's get rid of the g, multiply both sides by g. So we have t squared g is equal to 4 squared pi squared, or sorry, not 4 squared, just 4 pi squared times L. You can divide both sides by 4 pi squared, 4 pi squared. And we can cancel that out. So our length is going to be equal to t squared times the acceleration due to gravity divided by 4 pi squared. So this is going to be 2.0 seconds squared multiplied by 1.6 meters per second squared divided by 4 pi squared is just a number, and we can find that the required length of the pendulum to achieve a frequency of 0.5 hertz is 0.16 meters. Again, if we look at the number of digits in the question, we only have 2 digits available to us, so our answer is also going to only have 2 digits here.